Hi everyone, welcome back to Art of the Part. In this video, we're going to take a look at finite element analysis or FEA studies using SolidWorks simulation with revision management in mind. Now, we have the bracket exercise P1 open here, and we have a couple drawings that go along with this, so I'm just going to open them up really quick. And they go from P1 to P2 to P3, and what we're going to find out using these finite element analysis studies here is that as we apply loads to each specific iteration of this model, is that it's going to get stronger as we go through this. So P1, spoiler alert, it is going to fail, and it's going to fail pretty catastrophically. As we go into P2 here, we add some ribs, and it's going to get a little bit stronger. And then eventually here at P3, we want to get to a point that we actually are passing our finite element analysis and that we can run this part over and over and over again. So I'm just going to minimize that and just keep that in the back of my mind here. But the first thing that we want to do when we're looking at this bracket exercise P1 is define what material that we're going to be using. So over here on the left-hand side in the feature tree inside SolidWorks, we have this area here called materials. And if you right-click on this from the drop-down menu, you do have the ability to edit the material. So if you click on edit material here, it's going to open up this library of materials that we can use. And it might set you in a specific area like steels or iron or alloys or things like that. But if you scroll all the way up, you can actually close or compress down these windows with the little arrow here. And if you want to look for example, 6061 T6 aluminum, that is going to be here inside the aluminum alloys folder. So if you open or expand that out, this is going to be in numerical or alphabetical order. So as you scroll down here, we're going to be looking for 6061. And if you are having trouble locating where that 6061 or any other material type that you're looking for are, you can actually come up here to the search bar and you can type in the material that you're looking for. So for example, if I'm looking for 356 cast aluminum, there it is. If I'm looking for acrylic, I can find that like that. Or here for this example, we're going to be looking for 6061, and we're going to be looking for that 6061 T6. So go ahead and find 6061 T6. You can either scroll all the way down until you find it, or you can type it up here into the search bar. Just make sure that you click on it. And when you do click on that, you want to make sure that your units of measurement is currently set to megapascals. Now, my preference and how I've always run static studies or FEA simulations here is I've always used megapascals. Sometimes this might get into, for example, like just regular pascals, but you can see that these numbers are quite large for their tensile and the yield strength. Likewise, if you are working from IPS, you can see that the PSI values are quite high as well. These are almost like unobtainable numbers in my mind. This is why I always use megapascals, because if you hit this drop-down menu and you go to MPa, that's that Newton millimeter squared, so megapascals, you can see that these are pretty nice round whole numbers. Tensile strength is 310, yield strength is 275, and that's going to be important for us to kind of keep in the back of our mind too as we start to set up these static studies. And I'll just pull up a PowerPoint that I have from another class here explaining stress-strain curves. So we have two different definitions of when we're inside the stress-strain curve. We either are in elastic deformation or plastic deformation. Now, when you get to plastic deformation, this is the point of no return, and this is where the material is going past its intended load rating and it won't return back to its original shape or size. A good example of this is if you take like a piece of plastic and you bend it over and over again, you will see that maybe at the bend point it starts to turn white or it gets a little hot, and that is showing you that you're actually getting to this necking portion where it's actually going to split and separate. So this is past the point of where the material can return back to its original shape or size. So in my opinion, whenever you're trying to run a static study or design a part, you always want to be here in the elastic deformation, unless you are intending to break the part. So maybe it's like a snap break or something like that. But in most cases, and how I'm testing my materials, I pretty much want to be here in the elastic deformation, and I want to stay below this yield strength number. So just keep that in the back of your mind. We're just going to go ahead and minimize this, return back to the properties window here for the library. And again, something just to maybe write down or put somewhere or just memorize is just the yield strength for 6061 here is going to be 275, and then the tensile strength is 310. So we probably want to be working from this 275 number. So I'm going to move this window over here to the right, and when you change or update the material and you click on this little apply button right here, you'll actually see that the display of the component or the part will change. So I'm going to hit apply, and you'll see that the color has changed to update or correlate with that 6061 T6 material. So after you see that change occur, we can actually just go ahead and click close here, and now we have changed the material here for this specific part or component. As a quick double check, you can actually go over here to the Evaluate tab, and this is actually pretty convenient. I use this all the time, especially when I'm in the design process and I'm trying to stay below like a specific weight requirement. You can actually go over here after you apply the material and click on Mass Properties. And when you're in this Mass Properties window, it'll actually tell you what the mass of that specific component is, with the volume, the surface area, so on and so forth. And as a bad example, just sit back and relax for just 1 second. But if I actually go back in here at the material and maybe I change this to maybe a plastic, I'll do like ABS. And I click Apply, and I hit X here. So before it was like 0.09 pounds, and if I go to Mass Properties now the mass has updated to 0.03 pounds. So this has been pretty accurate in my opinion. I've cut material and weighed it after the fact, and I'm like within like 95% of what this is displaying here inside of SolidWorks. So whatever they're doing there to update these values, they're doing a great job. I rely on it quite a bit. So I'm just going to update this back to the 6061 T6 so that we can proceed on with this static study here. Okay, so we see 6061 up there, Mass Properties. We are back to that Mass Properties, 0.09 pounds. Okay, so we're just going to continue on here. I just wanted to show that little example, but we do want to move into the SolidWorks simulation or the FEA study side of things, and we are looking for a tab up here in the Command Manager ribbon for simulation. So right now we want to go to SolidWorks add-ins because we don't see that simulation tab, and if we want to populate that, we have to look for this icon called SolidWorks Simulation. It's going to be this little L block, and it's going to have a heat map that's red, yellow, blue, and green. If you click on that, just wait 1 second, but what this is doing is it's activating the add-in for SolidWorks Simulation, and you'll see that we're going to populate a new tab here for the simulation right there. So once that loads or it uploads or creates that add-in for you, you can go ahead and click on this tab for SolidWorks Simulation, and there's really only one option for us to select in here, and that's going to be create a new study. If you hit this drop-down menu, there is going to be this option for Simulation Advisor. I actually will advise you to not use the Simulation Advisor because I think it tries to push you in specific directions and pigeonhole you into certain selections, whereas if you do the new study, you can set this up exactly how you want it to, and you can manipulate the criteria that you're applying as needed. So I'm just going to go ahead and select New Study. And over here on the left-hand side, you'll see that we're creating a new static study by default. And on the left-hand side, as it's going down, depending on what package of SolidWorks simulation you have, you might have access to maybe 1 or 2 of these, or maybe like half of them, or the entire list here. But if you don't see these and you're trying to access a specific SolidWorks simulation package, you will have to go to your reseller and upgrade that accordingly. So here we're just going to stick with a pretty general static study. We will want this to link to the P1 bracket that we're working on right now, so you can rename this if you want to stay organized. So instead of it just being like a generic static study, we will change this to P1. And then we're going to create this static study itself by clicking on the green check mark from the top left-hand corner. So once you click this green check mark, you're actually going to see that the left-hand side of your property manager, or in this case, the feature tree, is split into 2 areas. So we have our feature tree up here, and then we have the property manager for this static study down here. Likewise, as you look down to the bottom, there are these different tabs. You have model, 3D views, motion study, and then P1. So if you're working on the static study, you're going to be inside this P1 tab. If you have to make any changes for whatever reason to this specific model, you can't make it here inside of this tab here for P1 because it's locking you to this specific static study. You will have to go and return back to the model itself, and then you can start making changes as needed. So just understand that if you're trying to do this dynamically and you do a study and then you add a specific detail, you change a specific detail, you have to go back to model, and then you have to go back to the P1 study or whatever study that you're working on, and then updating it accordingly. So just make sure that you're here inside the P1 tab. And I just like to have a conversation pretty much going down the left-hand side of the property manager of this static study instead of going through the advisor like I was talking about earlier. So first and foremost, I'm going to come up here to the top entry here for P1. So once you locate that P1, you can right-click on it. From this drop-down menu, I want you to go and locate an option here for properties. So we want to get to the properties of this P1 static study. And typically what I've always done, and I've been using SolidWorks simulation for the last 10 years here, I've always tested using large displacement. They just recently added this compute free body forces, and while there is some value into this, I do want to just teach this static study from its most basic principle, and I don't like having these variables with these sliders here where you have approximate or precise. Like, I'm just going to remove that from this entire equation and use large displacement like I have been doing for the last 10 years. So I'm going to click on this option here for large displacement. So go ahead and click on large displacement. It actually removes or turns off this contact penalty stiffness scale factor, and it turns off that compute free bodies forces. Additionally, I want to set up a location where my save result files are going to be saved to. So right now, this would save all of our results files into the file folder that this bracket exercise P1 is currently saved into. And if we're doing all these different revisions going from P1 to P2 to P3, we're going to have a lot of results files, and they might actually start to interfere with each other. So I think it's best practice to actually set these up in a file folder hierarchy. So you actually want to turn off the save results files to SolidWorks document folder. Go ahead and deselect that. You now have this ability to select this icon for select a folder to store the results file. Go ahead and click on that. And then we're just going to go to our bracket exercise FEA studies file, wherever we're saving our files here. And we're just going to set up a file folder hierarchy. So we're going to right click, and then we're going to go to new folder. And I'm going to name this new folder here FEA studies. And then I'm just going to go inside of this file folder here, and I'm going to set up a new file folder for P1, P2, and then P3. So I'll just do right click, new folder. I'll name this one P1. Do right click, new folder, P2. Right click, new folder, P3. Okay, so now that I have my file folder set up, I'm just going to go into the P1 file folder. So just double click on that. And then from the bottom right-hand corner, it might be blocked by my face here, but there's going to be an option here to select folder. And this is where we're going to save all of our results files. So just go ahead and click on select folder. And then we can see that we've set up this file explorer path to that new folder that we created. So again, just double check for me again that we are working from large displacement and that you have saved the results files to this new folder that we created. So as long as you have both of those set up, we'll go ahead and hit OK. All right, so we've satisfied that first criteria, the entry inside the properties manager of this static study. We're going to move down here into the bracket exercise P1. If you hover over this, this is actually going to be the display or the material that we're going to be using for the static study. We already did this in a previous step. However, if you had a change from 6061 to like 356, you're going from a forged material to a cast material, you can always right click this and then apply or edit the material and then update it that way. You can always apply like a draft quality mesh if it's like a big file, maybe a big assembly, and you're trying to reduce the computational limits of that. You can always do it like that as well. Sometimes this is a good check too if you have multiple bodies, because you'll see that there's going to be multiple entries for those body types, and you'll have to apply material type for each one of those bodies before the static study can run. So sometimes I've used like surfaces to apply like extruded cuts to, and I have to either go in and delete those bodies or remove them from the static study or apply a material to them so that they can be ran. If you do not have a material applied, it will not run the static study. So just throwing that out there. We've already satisfied this entry here for the material type, so we don't have to edit or apply this. We will move down here into connections. Now for this specific static study, we will not have to worry about connections. We don't really have like any specified bolts. When I am testing like other details, I do want the torque force of those bolts and what material those bolts are made out of. selected and defined. However, here we're just going to do a very simple general static study. We are not going to set up our connections. So we're just going to move down here into this next criteria, which is going to be fixtures. So I'm going to right click on fixtures here, and from the drop down menu of the fixtures, we have the ability to set up fixed geometry, rolling, sliding, hinges, elastic support, so on and so forth. Again, we're just going to keep this very simple. We're going to keep it very basic. We're just going to click on fixed geometry. Now, when you click on fixed geometry here, it is going to give you this little graphic on the left-hand side of this properties manager. And anything that we highlight or select in green, this is going to be a fixed surface or a fixed face. So we want to actually make a fixed surface or fixed face on each one of these through holes at the bottom of my part here, as if there's like a pin or a bolt holding them down into place. So I'm going to select on the through hole of these two bottom holes. When I click on that, you can actually see that it's being populated over here on the left-hand side. We have fixed geometry selected, and we have that one face. Now we will have to do the other through hole, so we will come over here to this secondary through hole, click on that, and now we have two faces considered for fixed geometry. So when we run the static study, these are going to be locked in place in 3D space, and everything else is going to move around it. So we'll go ahead and hit the green check mark. And we can see that there are little green arrows being applied to those fixed faces. If for whatever reason you had to delete or change these, you can just go back over here into the fixtures and you can right click on them and edit them as a feature, just like we would do inside the modeling aspects. So we're going to continue to move our way down here. We're going to go down to external loads. I do have this classified already inside of our drawing. So if you go back to the P1 drawing, we can see that I'm telling you to test to 250 foot-pounds from the 500 through hole location. So if we look at our model here, we have a 500 through hole at the top of our part. We are going to apply that load to that through hole. So we're going to minimize this, return back to our model here. And then we're going to go and right click on external loads. So when you right click on this, we're going to get this drop down menu, and there's a handful of different types of force that we can apply to the specific model. We can do standard force, we can do torque, pressure, gravity, so on and so forth. Again, we are just going to do a simple static study here. We're going to just click on force. It's going to be the default option here at the top. So go ahead and click on force. And we have the ability to apply force to specific faces. So inside this blue selection box, we are going to populate this with the 500 through hole at the top of our model. So when you hover over this, you can actually see these like purple arrows. This is the direction of where the force is going to be applied. So this will be a problem, but we will select on this 500 through hole to just at least populate that over here on the left-hand side in this selection box. So we have the face selected, however, these purple arrows are going in opposite directions. And if we were going to apply this force and run the study, we're actually going to expand that through hole, and that's not exactly what we wanted to do. With this model, it is pretty easy. If you wanted to, you could kind of cheat it and actually apply it to this like top base here so that the forces are applying down. But let's say for instance, we are trying to apply force going left and right, or maybe from a different direction. We really can't select on like this outside edge or this entire surface right here. So I want to show you a good practice of how to set up your force studies so that you can control what direction they are being applied to. And in this example, we are trying to keep it simple. I'm not trying to bring this into a big old assembly. And let's say we had a rod going down the part, maybe at the top of the rod there was going to be forces being, pressed down onto it. Maybe like an axle or something like that. And you can simulate that pretty easily using this method. So for example, after we've populated this face for the 500 through hole, we can change this from a normal force direction to a selected direction. So if you click on selected direction, you now have the ability to select on a face, an edge, or a plane for the forces to run along or be projected against. And this again, I'm kind of a broken record here, but always, always, always draw on your origins because you have access to all the planes that we've referenced before. So for example, your top, front, and your right plane. And if we find a plane that is going to run down the center of this model, we can apply force from that plane to this through hole going downwards. So we are going to populate this pink section here for the face or the plane or a surface. We are going to try and access that plane from this model. So if you go up here into the viewport or the graphics area, you can open or expand out the feature tree from this model by clicking on the little black arrow, or you can click on the feature manager design tree right here as well. But we're just going to click on this little black arrow It's going to open our expand out here. And if you hover your mouse over these different planes, we can try to find a plane that runs through this down the center of the model. So the front plane, that's out. Top plane, that's going across. However, the right plane is running right down the part, and we can apply forces from that right plane into that 500 through hole. So as long as we have this pink selection for the selected direction selected here, let's go ahead and click on right plane. You can see that the right plane has now been populated in the direction or the selected direction. And then we have to update our units of measurement to the foot-pounds that have been called out in the blueprint earlier. So inside the units here, we're going to change this from SI. We're going to hit the drop-down menu. We're going to go to IPS so that we can get our foot-pound measurements. And then over here, we now have this option to select from different forces or different directions that the forces can be applied to in relation to the selected direction of that plane that we just created. So I already know this off the top of my head, but if you wanted to, you can go ahead and click on each one of these and show where those forces are going to be applied from that plane. But I know it's going to be a long direction too, so that goes up and down. So if you click on a long direction 2, it's going to turn on this force direction here from this plane, and you can see that the arrows are now, instead of being projected outwards from the through hole, they're actually being pointed up. And if I wanted it to reverse and go down, we can actually click on reverse direction, and you can see that the direction is now going down along this part. And again, I'll just show a bad example, but sit back, relax, don't follow me here. But if I actually turned off this direction and I was trying to go right here, I can actually click on direction 3, and this is a good way, if maybe this bracket exercise or this bracket piece was being held up like this, and then a force was going to be applied or hit along the side of it, you can do so using this method. Whereas if you tried to select on like one of these edges here, or one of these surfaces, you'd apply that force basically along this entire edge or along that entire surface. So just a nice little trick on how to manipulate that force geometry as needed. So again, I'm going to turn that off, turn back on direction 2. Again, make sure that your reverse direction is there. And then we're going to update the force here to 250 foot-pounds. So I'm going to type in 250. And I've had this error happen a couple times for me, but if you hit enter, sometimes it defaults back to the 0.224 dimension or value for this force. So what I do is I just leave my mouse or the clicker inside of that selection there, or I click off of it, but I just want to hit the green check mark instead of hitting enter. So once I hit the green check mark, you can see that force is now applied to that through hole going downwards in that direction. All right, so this all looks pretty good so far. The only thing that we have left to do really before we start moving into running the study is to set up a mesh file that is going to correlate to this design that we created. So after we've satisfied all these different entries here, we're going to go down here to mesh. This is pretty much the last entry before we get to our results for this static study. If you right click on the mesh, from the drop down menu, we're going to go ahead and try to create a mesh. So go ahead and select create mesh, and then it's going to open up this properties manager here on the left hand side for the mesh creation. And again, I just noticed this happen over the last couple of years with the releases of SolidWorks, probably like 2021, maybe 2022. But they actually changed the default mesh parameters to, if you click on mesh parameters, they changed it to blended curvature mesh. And while this might be good, I think this is pretty much overkill for this simple static study here. It's a pretty simple part. We don't have multiple components running in the background. So I've always done, especially for these simple parts, I like to run quick studies, especially if I'm going from one revision to the next, or I'm doing this dynamically and I'm trying to use FEA while I'm designing. I just leave this in the standard mesh selection here. So when you go to standard mesh, this is how I've always designed. As I get to more complex parts, or maybe I'm doing my final test, then I'll go to blended curvature mesh. But here, I just want to do standard mesh, and we'll just go ahead and hit the green check mark. And this is going to take a second to populate, but you're going to actually see this turn into a true mesh file. If you're used to 3D printing, you're used to STL files, If you try to open them up into CAD, there are a bunch of little triangles. And this is where maybe the nickname comes from. I know STL is stereolithographic, but I've often heard it referred to as standard triangle language before, because as you look at this, it has all these little triangles that create this entire 3D model. Now, this is a very easy way to create a mesh cloud to apply forces and different node points and where those forces are going to be applied to. So this looks pretty good for us before we actually start to create this static study. Now, one thing I want to mention here before I actually run this is I'm going to go to my FEA study window here, where I go back to FEA studies, P1, and when we created these file locations, the file destinations for the static study itself, back when we right-clicked on the static study and went to properties, you can actually see that we created mesh files for that static study. So as you go from P1 to P2 to P3, you can see that these files might start to overlap. So I'm also going to keep this open up here in the background, keep this on the left-hand side, and then I'm going to go to SolidWorks here on the right-hand side. Go ahead and expand that out. And before I run this, I want you to pay attention here on the left-hand side while this is actually creating the static study itself. So after we have everything satisfied over here in the properties manager of the static study, we have the mesh file, the forces, the fixed, material type picked out, so on and so forth. We can come back up here to the simulation tab. And inside of simulation, I want you to click on Run This Study, which is the little block here, little L block, and has that heat map like we were looking at earlier. So when I click on Run the Study, again, I want you to pay attention here on the left-hand side. Click on Run the Study, and you can see as this creates this progress bar here, we've created all these items that are related to this specific static study. So as you go again from P1, P2 to P3, you can really start to overwhelm that file folder or put yourself in disarray and disorganize all these file types here. This is my preferred method, creating these file hierarchies, so that I know exactly what files or result files are linked to which static studies. Okay, so we ended up creating like 50 different files. They got compressed down here to 14 different files. These are more or less variables. You might have more or less files depending on how you're running your static study. But as long as you get a heat map generated over here on the right-hand side, I'm happy with it. That's exactly the result that we want to see. So I'm going to maximize this window and return back here to the static study itself. And at first glance, this looks pretty good. So we see a whole lot of blue on this, which is telling us that there's not a lot of stress or strain being applied to those areas, or maybe our part is stiff enough or strong enough to withhold those forces. And then as you go up this color chart or this heat map here, you're going to see it progress into green, which is starting to increase the stresses or strains or forces being applied to those areas. And then when you start getting into yellow, orange, and eventually red, that's probably where you're going to start to get into failure points inside of this model when you apply those forces. So again, this looks pretty good first pass, first glance. There's nothing terribly wrong with it. We might have a couple of areas where the model might fail here, where we start to see that yellow, orange, and red of the heat map. However, I do want you to kind of think back to what we were talking about with yield strength, tensile strength, so on and so forth, and where those stress strain curves were going to be applying points of plastic deformation versus elastic deformation. So if you look here on the right-hand side on our von Mises scale, we can see that the yield strength is set to 2.75. I'm thinking that that's probably going to correlate with that 275 megapascal number that we were thinking of earlier for yield strength. And we can see that that red arrow is actually right here in the middle of the green area of our heat map chart. So anything in the green area is actually going to be starting to get into that plastic and then into elastic deformation, and then everything afterwards is going to be that plastic deformation where the part is going to actually get to that point of no return where it can't return back to its original shape or size. So we have to kind of change the perspective of this test or the results so that we can understand it a little bit easier on where points of failure are actually going to occur. So what I want you to do is I want you to right click on this chart here on the right hand side. Likewise, you can also right click on the stress results on the left hand side, but as long as you right click on them from the drop down menu, there is going to be this option here for edit definition. So edit definitions right there. Likewise, if you come over here to the chart, right click on this from the drop down menu, you can click on edit definition there as well. So once you get into edit definitions, it's going to open up the properties manager of this result file here. And over on the left hand side in that property manager, we do want to make sure that we are working on the von Mies scale. However, the units of measurement is currently set to pascals, which is that newtons meter squared. So we want to change this back to that megapascals, that MPa value that we were looking at earlier when we were changing the material. So if you hit the drop down menu here for newtons meter squared, you can go and find the MPa value for newtons millimeter squared. So we'll go ahead and apply megapascals or newton millimeter squared. And then you want to move over here into your chart options. Now click on chart options. And what I always like to do is set up a max annotation so I know exactly where the most amount of force or load or stress is occurring on this model. So I just want to click on show max annotation. So I click on that and you can see that this is calling out the area where the max annotation of the force is being applied. And then likewise, as I go down this list over here on the left-hand side, I do want to change this from scientific notation, which is all those exponential values. You can see that the yield strength is 2.75 to the 8th power. And to me, those are just like unobtainable numbers again. Like, it just doesn't make sense in my head. I like to see things in very basic, simple numeric format. So I am going to update or change this scientific format here to general. So hit the drop down menu and we're going to look for this option here called general. And it's going to return us back to those values that we were seeing when we were editing the properties of the material itself and changing it to megapascal, where yield strength was 275 and it was a nice whole round number. And then we have 315 for tensile strength. So as long as we update this to the general value and we hit the green check mark, I want you to pay attention to what happens here on the right hand side for the chart that we're updating. So we'll hit the green check mark and you can see all those values have now been updated here to solid or whole numbers. And we see at the top of our chart here, we have a value of 438. So we're experiencing 438 megapascals on this part, which is nearly double what the yield strength would be for this specific material that we're using. So what I like to do, and this is pretty much consistent if you're trying to like update a chart or a table inside of like Excel or PowerPoint or Microsoft Word, you just want to come up here to that top value. So wherever it says 438, I'm going to update or change this here to that 275 yield strength number. So I click once, it's going to allow me to open or edit this, and I'm going to change this again to that 275 value. So if I type in 275, and we can see that this paints a much different picture. So what we saw before is maybe a minor stress point is now a critical failure point because this entire area is red. So that might actually break or snap, especially if it's all the way up here at that 438 megapascals value. Likewise, if you wanted to investigate maybe some other areas where it wasn't just looking at the max annotation, you can do so by coming over here to the left-hand side where it says stress. That's the current test that we're currently in. So I'm going to right-click on the stress test, and then from this drop-down menu, I'm going to locate an option or an icon here for probe. It's a little eyedropper. Go ahead and click on probe. And this is going to open up a probe property manager. And what's nice about this is I can actually click anywhere on this model and it's going to give me what the megapascal value is in relation to this chart that we just updated. So for example, if I click on this little green area right there, I can see that it's getting to 113. And as I move up this sidewall here, you can see that the value is changing from 113 to 162. And as I get closer and closer to this red area, I'm going to try to hit this yellow area here. I'm getting to 231, which is pretty consistent with that. And then once you start to get into this area here, it's getting to 382, and then eventually up there into 364, 382, and then the max annotation is going to be that 438 value. Now, if you hit the green check mark, it will keep those probes in place. However, I do actually want to click on the red X because I don't want to save them. I was just investigating that sidewall and seeing like how those forces or those stresses were being applied as they moved up to that critical failure point. So I'm going to hit X here. Another neat little trick to kind of see how this model is running or how this test is running is if you right click on that stress test once again, from the drop down menu there is an option here for animate. If you click on animate, you can actually see an animation of how that test or how the forces are being applied and how the model is reacting. So this is consistent with what I wanted to see when we were setting this up. We wanted these two holes back here to be fixed, so we aren't really seeing any stresses being applied there. However, we are trying to apply the apply the forces to this through hole, and this is almost creating like a lever arm, which is going to actually create an exponential value of stress back at these points here. So if you wanted to, you can slow it down or speed it up using this little slider bar here. If you wanted to, you could save this out as a movie file and send it to a client for somebody for approval, or explain it to another engineer if you're maybe working remotely. However, I'm just going to click X on this. I'm not going to save the animation. And then I just, again, want to return back and explain this chart here one last time as we move into creating another plot. So I am going to recommend or encourage you to always update this chart here to correlate with the yield strength value of whatever material that you're using, mostly because I want you to stay within the realm of elastic deformation. So that when you apply loads and forces, you want to make sure that the part or component always returns back to its original shape or size. And I referred to this earlier, but when you start to cross over this yield strength value, you get into this point of no return mentality where you start to enter into plastic deformation, where the part's going to get damaged or deform, or maybe start to crack, or once you even get to tensile strength or ultimate tensile strength, you'll actually see the part shear or break or snap like you would in a normal like dog bone test when you're testing the tensile and yield strength of a material. So just something to keep in mind, whenever I'm designing, I like to set this upper limit value here to 275 or whatever yield strength that I'm using for that material. And then I just try to use it as a frame of reference so that when I am looking at my result files, I want to make sure that this max annotation is a little bit below or well below, depending on what we refer to. And maybe you've heard this terminology before. We've called this factor of safety. So when you start to look at factor of safety, you probably have heard that like a specific part or component has a factor of safety of 1.5 or 2 or 3 or so on and so forth. And I'm going to use the example of a factor of safety of 2. Now, what that's saying is you're trying to take the intended load and basically double it, or make sure that the part or component can withstand twice as much force or twice as much load before it actually breaks. So if I wanted to run this test, I could frame it in a couple different ways. If I wanted to see this at a factor of safety of 2, I could probably change my force value here from 250 to 500. I'm just like doubling it. And then I would try to make sure that I'm well below 275 for my yield strength so that I don't enter into plastic deformation. Another way that we could frame this is we could take that 275 value and I could change this upper limit value here from like 275, and I could divide this by 2, and then I could say that that would be 137.5. And then anything that's above 137.5, that would then be outside of the range or my limit of my factor of safety of 2, because I'm setting the limit here of yield strength 275 divided by 2 to get that 137.5 value. So there's a couple different ways you could kind of frame that and look at that. Another way or reference that we could look at that too is if we actually create a factor of safety plot here inside of SolidWorks. And it's quite easy to do. There's a couple ways you can do it, but if you go over here to the left hand side where it says results, and this is where your stress and displacement and all that fun stuff is, but if you right click on the results section, it's going to open up that drop down menu again, and we can look for this option or icon here for define factor of safety plot. So let's go ahead and click on define factor of safety plot. And this is going to open up the properties manager for factor of safety. And what I'm going to encourage you to do is actually change some of these values here. So right now it's currently set to automatic. And I'm going to hit the drop down menu here, and I'm going to change this here to the von Mies scale, just like we were using before in the stress strain. We're going to go change this to von Mies. And then we're going to go ahead and change our upper limit for the factor of safety. And like I was saying, I'm going to use this like nice easy number here, factor of safety of 2. We're going to set the upper limit here. We're going to hit the check mark and turn that on, and we're going to update this to 2. And then we're going to actually come up here to the top of this property manager, and there's this little blue arrow for next. I'm going to go to next, and we just want to make sure that this is currently reading in the correct units of measurement. Currently it's set to just standard pascals. Let's hit the drop down menu. We'll update this to megapascals. And this again is more or less like how you want to perceive your factor of safety plot. Do you want it to be built from the yield strength, or do you want to be built from the ultimate tensile strength, or do you want it to be at a specific user defined? Like I said, my brain, my mind is always going to be set to staying within the elastic deformation. I think that's a really good place to be, because you always have that little extra bit of room before the part will experience critical mechanical failure. So I just like to stay within that elastic deformation state of the material type. And I'll leave it in the yield strength here, and then we'll go ahead and go to next. And then this is just like a standard factor of safety distribution. You can leave it at 1. That's totally fine. We'll go ahead and hit the green check mark and create this. And you can see here that the chart that we were looking at before is almost in reverse now, where the upper limit is where you want to achieve that level of factor safety. So everything in blue, that is saying that you have a factor of safety of 2. That's what we defined. Everything in blue meets or is exceeding that factor of safety of 2. And then once you start to see this discoloration into the heat map of maybe a lighter blue, green, yellow, orange, and then red, this is telling us that we're 6 times over that factor of safety. So we're actually at a factor of safety of 6, where that material is entering into like pretty much critical failure. So you want to make sure that you're at that factor of safety of 2, and you want to see this entire model be shown in blue, and that's going to give you the all clear that it is going to meet the intended factor safety value that we just set up. So if you want to jump back into your stress plot, you can actually go up here from the factor safety test, go back into your stress, just double click on it, and you can return back into your stress test. And I'm going to say that's pretty good results for our bracket exercise P1. I already told you at the beginning that I knew that this was going to fail, and we want to go through these series of revisions going from P1 to P2 to P3 to hopefully improve the overall strength and integrity and mechanical properties of this model as we add additional details or pieces of geometry. So I'm going to save this and call this complete for bracket exercise P1. I'll go up here to File, Save. Now, this workflow that I'm about to show you is a really good method of maintaining all of the criteria and settings from this static study for P1 so that I can carry over into the next revision and that we're testing apples to apples. So what I'm going to do is I'm actually going to do a save as on the specific SolidWorks part file. We're going to come up here to the top left-hand corner. We're going to go to File. We're going to go to Save As. And then we're just going to go to wherever we are saving our files here, and I'm going to change this from bracket exercise P1. I'm going to change this to bracket exercise P2. I'm going to hit enter. And this is going to be very important, but whenever you're doing the save as method, you always want to make sure that you are not copying the results files. Now what this would do is if you hit yes, this would actually link all of the results files from P1 into P2 and vice versa. You actually want to separate these. You want to create your own results files for P1 and your own results files for P2 and so on and so forth. So we will want to click on no here. So make sure that you're clicking no when this results files comes up. So click on no. And then we want to make some changes per the drawing. So I'm going to return back to my PDF here for the bracket exercise P2. And we can see here that going from P1 to P2, we have added this revision here for these additional ribs for strength per testing. So that's the revision that's being called out here in revision B. And we can see that it has a typical wall thickness of 125 thousandths. It has an included angle of 60 degrees, and it's starting down here at the midpoint, basically in line here with the origin. So after I've saved this here to bracket exercise P2, I can't make any changes because I'm currently still here inside of the results file of the static study. I do want to move back over here from these tabs in the bottom left-hand corner into the model itself. So I'm going to go here to the model. And we're going to use a pretty neat feature here. I'm also going to change or revert back here to the features tab inside of my command manager, but we're going to use a pretty neat feature here from some sketching geometry. So I actually want to start a sketch here on this top surface of this thin wall here. I'm going to right click on it after it's highlighted or selected in blue, and I'm going to start a sketch. This is going to then reorientate my part so I'm looking head down on it. And then I'm just going to create a couple of lines here. I'm going to go inside of my sketch tab. I'm going to go and find the line tool. It's the first icon on the first row. Hit the drop down menu, and we're going to go and find the center line tool. So click on center line. We're going to snap this to the origin or link this here to the origin. Click once, and then we're going to drag this down, and we're going to snap it to the midpoint of this bottom edge. So we'll click once or for the second time down here. And then instead of going back and forth between different line types, I'm just going to stay here within the center line tool. And then I'm just going to link this to the inside edge of this thin wall feature here. Be careful that you don't accidentally click on the midpoint. There is actually a midpoint relation to this arc or this line here. We want to be maybe a little bit below that, but we're just going to click that so that it's coincident with the arc itself, but it's not on the midpoint. Now, I don't want to draw any more lines here, so I'm going to hit escape a couple times on my keyboard. And instead of going back and forth between like solid lines and center lines, all I have to do after I created these two lines, I'm just going to click on this center line right here. And after it's highlighted, I'll right click on it, and then I have this ability here to toggle it from construction geometry to solid geometry. So I'm going to change it here to solid geometry. You can see that the line has changed from dotted to solid. And then I will just mirror this over. So I'm going to come up here into the sketch tab. I'm going to find my mirror entities icon, click on mirror entities. Entities that we're going to mirror, we're going to click on this one blue solid line, and then we're going to mirror this about the center line that we just created. And then we'll hit the green check mark. From the drawing, we saw that this was a 60-degree included angle. So I'm going to go over here to Sketch, go to Smart Dimensions, and we're just going to click on this line and then this line. And then I might have to escape a couple times. Smart Dimension, maybe I'll still draw in there. And then we're going to go ahead and give a value here of 60 degrees. Okay, so we'll hit the green check mark. We have fully defined our sketch here, and we're going to use this really neat feature. Instead of moving into like an extruded cut or an extruded boss base, we're actually going to use a feature here called ribs. So from the sketch tab, we're going to move over here into the feature tab in the command manager, and you can see that a lot of our features are actually turned off because we don't have watertight geometry available to us. We only have two single lines, and we are actually going to go and select on this rib icon right here. So it's about halfway down the middle here, and it's on the top row. We're going to click on rib. Click on rib, and what's really nice about this rib feature is it recognizes that we want to use these lines as reference for the ribs, almost like a thin wall extrusion. However, we have the ability to change what direction it's extruding, if it's going to be on one side of the line or the other side of the line, or maybe you want to make it bidirectional, which is where you typically would want to be for most ribbing commands. So over here on the left-hand side in the Properties Manager of this rib command, we want to make sure that our thickness is set to this middle icon, which is going to be the bidirectional or both sides. We're going to update this to the typical wall thickness of 125 thousandths that we saw on the blueprint. And now we have extrusion directions. So you can see from the reference of this arrow, it's going to the outside. We actually want to change this so that it's going down. So from the extrusion direction, we can actually toggle this to this second icon here to normal the sketch. And you can see that we have a preview or projection of how this is going to create the ribs. Now, I am going to zoom in here and kind of explain this, but you can see from the projection of this extrusion for the rib, it's actually going to be outside of this thin wall. Likewise, over here, we don't have this projecting all the way to the edge of this thin wall of the interior pocket. However, when we hit the green check mark, the rib feature is actually really smart and it's really dynamic, and it recognizes all the different geometry inside of your model and is going to try to create what's the best option for this rib command. So when I hit the green check mark, it's actually going to trim off the excess here of the rib that would be outside of the thin wall, and then what was missing here, it's actually going to extend it to make it coincident or intersect with the inside arc of this pocket. So this is a really useful tool, especially if you're trying to do like plastics or other mold components. And speaking of that, you can actually right click on this feature, and I'm just going to show you a bad example so you can just sit back and relax and watch. But as I open or go back into the edit feature of the rib command, I can turn on the drafts, and I'll use this as a pretty exaggerated example, but let's say I go to like 15 degrees. Look how easy it was to create drafted walls at 15 degrees from that simple rib command, only using maybe like 2 sketches or 3 lines, 2 solid lines. So I'm going to go back into that rib command, edit it, and turn off these drafts here, and the green check mark, and return back to here. Go back to there, change this back to 0, just turn off my rib. Oops, select the contours. There we go. All right. Top view there. Now, what we want to do when we're looking at this rib command is we want to also add or include, as we look at the blueprint, the additional corner radii that are being projected throughout the model. So we have a typical corner radius of 135 thousandths there, and we already have that in place from a previous fillet command, which is going to be located right here, and we can see that that is 135 thousandths. However, we want to apply this so that this fillet command will drive the radii that are being projected from this rib. And what's really nice about the feature tree inside of SolidWorks is that you can click on these different features and you can reorder them as needed in whatever chronological order that you need, so that you can apply maybe these fillets to these corners. So if I click, hold, and drag on this rib command, I'm using the left mouse button. I'm going to click on that rib feature, and you can see that it's attached to my mouse, and I get this little arrow that's going to like loop back below a certain selection point, and it's going to drop that rib command wherever I release my mouse. So again, I'm click, holding, and dragging, and I'm going to pull this above the fillet 1 command but below this additional extrusion. And if I drag this right after this boss extrude but before this fillet command, it's actually going to drop this rib right there. And as I go back and edit the feature for this fillet 1, I can right click, edit the feature. I can actually see the fillet command, whereas if I didn't drag this, I would only see the pocket without the ribs because the ribs came after the fillet. Now we put it before the fillet, and we can include these ribs or these corners from the ribs inside of this fillet command. So just be very careful and make sure that you are selecting all these additional corners here or all these additional intersection points where the ribs are meeting up with the thin wall from the shell, because I've had this before where students do not select all of the corners, and they're going to get really skewed results from their FEA studies because they have a sharp shear point rather than a nice flowing radius. So just make sure that you double check that we do have this fillet applying to all these corners here, and then we'll go ahead and hit the green check mark. So that looks pretty good to me. And what we're going to do now is, after we've made or satisfied all the changes going from P1 to P2, is we're just going to return back to our static study and just update some of the criteria so that it's linked to this specific model. So as you look down here on the bottom left-hand corner, we are still currently inside of the model tab. If you go over to where we created that P1 static study, we are going to rename this. So I want you to right-click on that P1 static study. And from this drop-down menu, I want you to, let's go over here. Maybe you have to select on it first. Yeah, select on it first, then right-click on it. And then you're going to right-click and select Rename. We're going to name this P2. Hit Enter. And you can see that we've changed or updated the name of that static study from P1 to P2. Likewise, and make sure again that you are inside of the static study itself or this tab down here. You can see that the P2 result files and all the details that are linked to it are now linked underneath that P2 static study. If we right click on that, we're going to return back to that properties window. So we're going to go back into properties from this P2 selection. And again, we just want to double check that we are still working in large displacement. That all looks great. And then here inside the results files, this is still currently linked to the P1 results files. You want to relink this to the P2 file folder that we created earlier. So you want to click on the select file folder to store the results. And then we're just going to return back to the file for the FEA studies. And then we're going to find our file folder for P2. So we'll go ahead and double click on P2. We'll just select folder on the bottom right hand corner of this window. And we've updated the path of where the results files are going to be stored. So go ahead and click OK. And then we're just going to go down this list here and just double check, make sure, okay, it looks like our material is still current. It's still the 6061. The fixtures are still those 2 through holes at the bottom of the model. The force is still the 250 foot-pounds going downwards through the 500 through hole. And the only thing that really has to get updated here is the mesh, because the mesh recognized that we changed geometry from the original model and the existing mesh file is out of date. So this is kind of a cool thing that we can do now, because after we've set up this mesh previously, we can actually right-click on this mesh selection. So right-click on mesh, and from this drop-down menu, because we've updated and changed it to that standard mesh, we can just move into here and do mesh and run. And this is going to do the meshing and the running of the FEA study all in one click. So if you click on mesh and run, it's actually just going to go and mesh the file. So you see a progress bar, and then it's going to bring up a secondary progress bar for the static study itself. And you can see where we were before, like 427 or 428 megapascals for the upper limit of this FEA study. And just by adding those 2 additional ribs, we've made a major improvement and brought the max annotation value down to like 307. So even though that this is past the yield strength, you're entering into that plastic deformation, this is still below the tensile strength of the model. So even though that this will probably deform and get damaged, it's actually not going to catastrophically fail as it was seen before when we were in the 400s of that megapascal value. And what's really nice about this whole method and this workflow that I was just showing you is you probably were thinking about it as we were like running this, but you didn't have to set everything up again because you did that save as. You basically made a copy of everything that we finished in P1 and you moved into P2, and now you have all the same criteria, all the same settings. You didn't have to update the edit definition of this table, and we're all good to go. You just have to go and add your geometry and then mesh and run. Likewise, we have our factor safety still set up, and you can see the factor safety is improving quite a bit. Before, this entire area was shown in some discoloration, and now we just have discoloration in these 2 areas right here, or 4 areas if you're looking at it in a symmetrical sense. So if we return back to the stress here, we see that we're currently at 307, and we have one additional revision to go through to really make this model as strong as it can be. And obviously we can make additional changes, but it's going to be an even bigger improvement going from P2 to P3 and the overall mechanical properties of this model. So let's go ahead and make sure that we are saving bracket exercise P2. We're going to come up here and do File, and we're going to go save this. So we saved from P1, kept all the results files there. We saved from P2, kept all the results files in there. And now we're going to do an additional or last save as so that we can separate the results files going from P2 to P3. So we'll go up here to File, Save As. And again, we're going to change this from bracket exercise P2 to bracket exercise P3. We'll hit Enter. And again, we want to make sure that we are not copying the results file, so we're going to hit No. And then we're going to return back to the model. So we've created this new file here for bracket exercise P3. We're going to go over here to the model. And there are a couple additional details as we look at this new blueprint. We can see that the datum has changed. It's gone from P2 and P1, where the datum was at the bottom of the part, where now we're changing the datum to the midpoint of the entire model, and that we are going to try to maintain some form of symmetry by this GD symbol up here and right here, so that the part is symmetrical from one side to the other. And this is really going to make this part as strong as it can be, because we aren't relying on the strength of maybe one flat backside wall, where now we are basically creating a cross section and creating what like we would see in like construction or any other like building materials where you're I-beaming something out and you're really trying to make it as light as possible and as strong as possible as well. So we're creating this symmetric piece of geometry and we're just going to update the datum here as well. So I am going to return back to my model. We are going to go through a series of revisions here, but I'm going to go into my initial boss extrude, and if I want to kind of go back in time and look at each one of these features one at a time, I can use this rollback bar here. It's this bottom blue bar. If I click, hold, and drag on it, there's like this little pinch icon. If I click, hold, and drag, I can pull this all the way back to Boss Extrude 1. All right, so right now, if I look at this model and I look at where the top plane is located, it's at the bottom of the part that is correlating to the datum A. I'm also going to return back up here to the features of my command manager, but I am going to update this so that the part is basically being extruded from the mid plane. So I'm going to right click on Boss Extrude 1, I'm going to edit the feature, and instead of it being a blind extrusion, I'm actually going to hit the drop down menu and I'm going to make this a mid plane extrusion. So this is now going to change basically where my datum A is located so that it's being extruded equally from that surface or from that plane. So we'll hit the green check mark. That's good. Shelling. So the shell is fine, however, we do have to remove this additional shell or this additional surface back here. So if you go into the shell command, we'll right click on that, edit the feature, and whatever is highlighted in blue, that's being removed from the shell. I'm going to go ahead and select on this back face here, so we're going to remove both of these faces, and we're just going to be left with the thin wall of the model. Now we do have to add an additional extrusion, which is going to be the body of the mid-plane extrusion, which is this 250 thousandths from the extrusion right there. And this is going to be very important as you look at these blueprints because it is typical wall thickness of 125 thousandths unless specified otherwise. So we can clearly see that this wall thickness is 250, so that's outside of the range or outside of the classification for that typical wall thickness. So even though that typical wall thickness is 125, this dimension is superseding that call out. So just keep that in mind. All right, so we have to add additional extrusion here, which is basically going to be another mid-plane extrusion going 250. We're going to go ahead and select the top plane. We're going to start a new sketch there. And this is why I like to separate all my sketches into their own classifications or their own entities here, because instead of trying to convert entities or edges, I can just click on the outside sketch, have that all selected in one selection there. I can go ahead and click on Convert Entities, and it's going to pick up all those entities in one shot. So I really like that method there, and it's linking back to the outside sketch that was driving the previous Boss Extrude. And now I'm going to go to Features, we're going to go to Extrude Boss Base, and then we're going to make this a value of 250. And again, this is blind, so it's going one direction. So you can see the preview there, but if we change this from blind to mid-plane, we can actually see it go both directions. We'll select the green check mark, and then we'll go ahead and continue to move down here. We have a Boss Extrude, so we're just grabbing this rollback bar and we're just dragging it down as we're updating these features. So I'm going to go back into this Boss Extrude, right click, edit the feature. We're going to change this from a blind extrusion. Again, we're going to change it or update it to mid-plane. So it's still 625, it's going both directions there, green check mark. That's still looking pretty good. Now we have this rib command. So that rib looks pretty good right there. Now I have had some issues in the past where I can't mirror the rib and the fillet together. I have to do the rib first and then I'll do the fillet afterwards. So at least we can mirror the fillet so we don't have to draw all those sketches over again. So up here in the command manager, we're going to go to the features tab. We're going to go to mirror. So click on mirror. And then inside the mirror command on the property manager on the left-hand side, the mirror face or plane, we're going to open up or expand out our feature tree. We're going to find the top plane, which is going to be the datum A or a point of symmetry. So we'll go ahead and select top plane for our mirror face. And the feature that we're going to mirror is going to be the rib itself. So you can either click rib from the feature tree here, or you can click on the rib piece of geometry as well. But I'm just going to click rib right here, and then we'll hit the green check mark. And that is projecting pretty good. We can see that on the back side. And now we will just have to update our fillet command. So I'm going to pull down my fillet command here, and I'll go and open up or edit the feature for this fillet. And I can pretty much do this one by one, or I can have my selection bar on. But if I click on maybe this corner right there and leave my mouse there, I can see if it will pick up all the additional missing corners. So it's getting some of them there. That seems to be the remaining ones, so I can click on this icon. For me, it's the fifth one. It's going to be connected to the end face, so if I click on that, it's going to pick up the remaining corner radii, which is pretty nice. Again, I was able to basically make an additional 13 selections for a total of 16 edges. or sorry, 26 edges to project all those radii. We'll hit the green check mark. So we have radii on both sides. And now I just have to add the floor radii. So if we look back at our model, going from P1 to P2, or sorry, P2 to P3, we can see that we have floor radii being added to all these corners or the floors as well. So previously there weren't radii there, or anywhere on this floor. However, if we look at P3, we can see that there are radii being projected on all the top surfaces of the model, with the exception of the top surfaces of the extruded holes. So I do have to apply this typical floor radius of 0.0625 or 0.0623 in each one of these corners or floors where the wall meets a perpendicular surface. So we are going to go back into our features here. We're going to go and activate the fillet tool. And then I'm just going to pick on these and change this value here to 0.0625. Which is going to be the corner radius of a bullnose end mill. We'll talk about that a little bit more when we start getting into the programming aspect of Mastercam. So from this selection here, looks like maybe I can get some of these top surfaces like so. So connected there. You do that to this one as well. And then I'll get those. And then I'll just have to pick on some of these missing ones. So these back corners here, and then we'll be able to get all these floors pretty easily as well. Now these floors, I'm just going to select on these faces, 1, 2, 3, and we'll do the same thing on the top side. We'll do 1, 2, 3, and then we've added those floor radii to all the applicable floors. So let's go ahead and hit the green check mark. If you want a double check as you're doing those floor radii, it looks like I have a total of 12 edges, and then I have 6 faces. So if you want to use that as reference, so that you make sure that you have all the edges or faces selected, again, 12 edges, 6 faces. Hit the green check mark, and then we're just going to pull the rollback bar one more time to finish up with these cuts. And we can see that the cuts are going through both sides. Just make sure, I'll edit this here. If your cut was projected from the bottom surface, you would have to update this from through all to mid plane or through all both. Just keep that in mind, but I'll just do through all because it was built here from the top. Okay, and then I'll hit the green check mark, and I have everything pretty much updated going from P2 to P3. While there were quite a few more changes, and this is a more difficult update, you can see that we are making a much more complex part, and hopefully all of this effort is going to pay off because we want it to be even stronger than it was in the P2 model. So let's see what happens here. Just like what we did before, we're going to follow that same exact workflow down here in these bottom tabs. We're going to go over here to P2. We're going to click on that. We're going to right click, and then we're going to rename it. We're going to update this to P3. And pretty simple process. We're just going to go ahead and right click on the P3 model up here. So right click on P3 from the drop down menu. We're going to go to properties. Inside of properties, we're going to update or change the results file folder. We're going to click on that little icon right there. We want to make sure that we are not saving this into the P1 or the P2 file folder. So we're going to go back to our FEA studies. We're going to go into P3. We're going to select that folder right there. We're going to hit OK. And then we're going to go and just update the mesh and rerun it as necessary. So we're going to go over here to Mesh, right click on that mesh from the drop down menu. We're going to mesh and run one last time, and we're going to see if all these additional changes or revisions have improved the model and the strength of it. So we'll go ahead and mesh and run. Okay, so it's creating the mesh for us. We're now in the solver. And fingers crossed here, but we should see a much bigger improvement. And we can see that we are at 272 for our max annotation. So we made an even bigger improvement going from P1 to P2 and then P2 to P3. So now we're well within our yield strength value, and we're still working inside of the elastic deformation state of this material, of this part, of this component. If you go over here to our factor of safety, we should see that we're working pretty good here. We do have some discoloration for factor of safety of 1, mostly because this does make sense because we are only reaching the factor of safety of 1, which is 275. If we wanted this to be a factor of safety of 2, we would have to have the max annotation be 137.5. So this is registering correctly. Everything in 2, or everything is blue, is registering as that factor of safety of 2. However, everything in the red here is at least meeting a factor of safety 1, and we aren't going above it. So this is still a part that would pass, but it wouldn't have like any higher classification for factor of safety. However, when you start to get into additional models for your homework, and especially the midterm, we will start to see these results change quite a bit. So that should complete the revision management process going from P1 to P2 to P3. Likewise, you can see how we used FEA studies and SolidWorks simulation and static studies to really see how we can improve this part and where we can improve the part. We added the ribs to kind of mitigate some of the heat map or the stress that we were getting right here. And then even after adding the ribs, we added some radii to kind of make those forces flow a little bit better because they weren't reaching shear points or sharp edges of those perpendicular floors and surfaces. So I think we made a pretty good improvement going from P1 to P2 to P3, and I hope that this was useful and that you can use this going through like other models or other parts in your career. So I appreciate you sticking through this one. I know it was a lot of information, but hopefully you learned a really good workflow and a really good methodology as you start to use SolidWorks simulation with your design process. So thanks for watching, and we'll go ahead and catch you in the next one. Bye.